In the earlier lectures, we have seen the different characteristics of transmission line. In this lecture, we discuss the basics of Smith chart. A Smith chart is a graphical aid which is very useful in solving transmission line problems, and it provides a useful way of visualizing transmission line phenomena without performing detailed numerical calculations. This chart was developed by P. Smith at Bell Laboratories in 1939, but even though this chart was developed long back, Smith chart is included as a part of many modern CAD software and test equipment. So, Smith chart is being extensively used till date for solving various transmission line problems. Now, let us see how this Smith chart is organized. We know that the reflection coefficient gamma at the load is given by ZL minus Z0 divided by ZL plus Z0. If we normalize the load impedance ZL by Z0, then we can write normalized load impedance as 1 plus gamma divided by 1 minus gamma. Now, let us denote this normalized load impedance by its real and imaginary parts RL and XL. So, ZL by Z0 is RL plus JXL and gamma is equal to gamma R plus J gamma I, where gamma R and gamma I, they are the real and imaginary parts of the reflection coefficient gamma. Now, if we substitute this gamma here, then we can write RL plus JXL in this form 1 plus gamma R plus J gamma I divided by 1 minus gamma R minus J gamma I. Now, what we can do? We can multiply the right hand side by conjugate of this term both at the numerator and at the denominator. So, once we do that and we simplify, so this becomes 1 minus gamma R whole square plus gamma I square, and this term we can expand, and once we separate the real and imaginary parts, we get normalized resistance RL is equal to 1 minus gamma R square minus gamma I square divided by 1 minus gamma R square plus gamma I square, and similarly XL is 2 gamma I divided by 1 minus gamma R square plus gamma I square. Now, these two equations are very important in developing the Smith chart. So, we take the expression for the normalized resistance, and this equation can be rearranged in this form. Then, if we divide by 1 plus gamma RL throughout, then we can put this equation in the form shown. Now, by adding RL divided by 1 plus RL whole square on both sides, we get this equation, and from this we get gamma R minus RL by 1 plus RL whole square plus gamma I square 1 by 1 plus RL whole square. So, we can see that this gives us a circle if we plot it in the complex gamma plane. We find that the center of the circle is given by R L divided by 1 plus R L and 0. So, let us see how these circles look in the complex gamma plane. As I have said, the center is R L divided by 1 plus R L 0 and the radius is 1 by 1 plus R L. So, for different values of R L, if we plot these circles in the gamma plane, this is gamma r and this is gamma I axis. So, we can see that for R L equal to 0, we will get this circle. So, this is the R L is equal to 0 circle, and if we take R L is equal to 0.33, then we get this particular circle. So, in fact, one can R L is equal to 1 gives this circle and R L is equal to 3. Finally, we observe that as the value of R L increases, the radius decreases, and finally, when R L tends to infinity, the circle becomes a point here. And for R L equal to 0, we get a circle in the gamma plane with radius equal to unity. So, please note that this circle has the outermost circle has a radius of unity, and all other circles for different values of R L, they pass through this point gamma r is equal to 1 and their radii keep on decreasing. In the same manner, if you consider the expression for normalized reactance X L, then we get one minus gamma r square plus gamma I square is equal to 2 gamma I by X L. Now, what we can do? We can add one by X L square on both sides, take this term to the left and rearrange, then we get an equation of this form gamma r minus 1 square plus gamma I minus 1 by X L square is equal to 1 by X L square. Now, this equation again gives rise to a set of circles as we take different values of X L. So, let us see how these circles look. So, here once again this is the gamma r axis and this is the gamma I axis. Please note that the centers of all these circles will now lie on gamma r is equal to 1. So, this is shown by this dotted line gamma r is equal to 1, and then for example, please note this radius is 1 by X L. So, smaller the value of X L, larger will be the radius. So, for X L is equal to 0.67, we have this circle. For X L is equal to 1, we get this circle. For X L is equal to 2, we get this circle. So, we see that as X L becomes larger and larger, we are approaching towards this point. In fact, X L is equal to infinity will bring you here, and as X L becomes smaller, this circle it becomes larger and the radius becomes larger and the center moves over this line. So, finally, when X L tends to 0, this circle will pass through this line. We notice that we have two sets of circles. We find that X L can be positive or negative. So, based on that we will get these two sets of circles, and here we see that For negative XL, the centers move in this part of the gamma r is equal to 1 line. Now, for a given ZL for a passive load, we know that mod gamma is less than 1. Therefore, our area of interest in the complex gamma plane is within the circle which is defined by mod gamma equal to 1. So, if you revisit, here you can see that this region is the region of interest. So, if we retain this part only, in a Smith chart, this area of interest is represented graphically by two sets of intersecting circles. One set of circles corresponding to RL in the range of 0 to infinity, other set corresponding to XL in the range of minus infinity to infinity. So, if we draw these circles, the Smith chart will look as shown in the figure, and here you can see that these circles are constant R circles, whereas these arcs, they are part of the constant X circle, and we have the negative values represented here for the reactance part. Now, once we have this chart, we can now plot impedance on this chart. Please note that we can plot the normalized impedance, and the actual impedance can be obtained by multiplying the impedance shown on the chart by the characteristic impedance by which the impedance has been normalized. So, let us start with an example. Let ZL is equal to 100 plus j 50 ohm and normalizing impedance Z0 is 50 ohm. Therefore, our RL normalized resistance part is 2 and XL normalized reactive part is 1, and this point is shown on the Smith chart. So, this is the point which is determined by the intersection of R is equal to 2 circle and X is equal to 1 circle. So, this is the point denoted by the normalized impedance, and if you put a line from the center of the Smith chart to this impedance point, then the length of this line represents the magnitude of the reflection coefficient gamma. Also, this angle represents the angle of gamma, angle with respect to this axis, that is subtended by this line. So, either from this point, now we find that we get a direct measure the length of this line as the magnitude of the reflection coefficient, and this is theta or angle of the reflection coefficient. Now, here we have represented Smith chart by only few circles. The actual Smith chart that is used in practice for doing transmission line based calculations contains a large number of values for both R and X, and there are certain additional parameters which are provided in that chart, which helps in doing transmission line calculations. So, let us see a practical Smith chart. So, here you can see that the resistance circles and the reactance circles, they are very closely spaced and their values are indicated. For example, this is R is equal to 0.1, R is equal to 0.2, R is equal to 1 circle, R is equal to 2 circle, R is equal to 5. So, all these circles, these values are provided. Similarly, here x is equal to 1, x is equal to 1.6, x is equal to zero point 0.5. So, you can see that all these circles are very closely spaced now, and this part of the Smith chart, it represents the inductive reactive component, that means J x by Z naught, when it is used as an impedance chart. Smith chart can also be used for calculation of admittances. So, this part will also represents J b by Y naught. Now, we can see that here at the periphery of the chart we have the wavelengths marking. Please note that in a Smith chart, if you move around the center of the chart, make a complete circle, then essentially a lambda by 2 distance is covered on the transmission line. Now, here you can see the markings are wavelength toward generator. So, for any clockwise movement, essentially it is wavelength towards generator. We move from the load towards the generator, and if you draw a line from the center of the Smith chart intersecting these circles, then the wavelength that has been covered can be read directly. Similarly, we have, if you move counterclockwise, it is wavelength towards load. Please note that its 0 starts from here and then it increases this way, whereas wavelength towards generator, here is the 0 and wavelength increases in this way. And finally, this whole Smith chart covers lambda by 2. There are some additional scales provided which help directly computing several other parameters like SWR, return loss, magnitude of reflection coefficient. So, these parameters can be directly computed from the Smith chart. Let us now see how we can utilize this Smith chart for determining the input impedance of a transmission line which is terminated by some load. So, we know that in terms of the reflection coefficient, the input impedance Z in can be written as Z naught 1 plus gamma e to the power minus J 2 beta L 1 minus gamma e to the power minus J 2 beta L. Now, if we plot the load reflection coefficient, this gamma, and then normalized input impedance at a distance L from the load can be found by rotating the point clockwise around the center by an amount 2 beta L. So, please note beta is 2 pi by lambda, and when L is lambda by 2, we get a phase shift of 2 pi, that means a complete rotation. Now, let us illustrate how we find the input impedance by taking an example, and we consider the case when ZL is 10 plus J 25 ohm and Z naught is 50 ohm and L is lambda by 5. So, here in this chart, this is the starting point ZL, which is 0.2 J 0.5. If you divide 10 plus J 25 by 50, you will get 0.2 0.5, and from this point, now if you draw a circle, this circle will be called the constant VSWR circle. So, any point on this circle has the same magnitude of reflection coefficient and therefore, the same value of the VSWR. Now, starting from this point, as we move along this constant VSWR circle, the movement is indicated by these small circles, and we reach at this point. Now, you know that from the wavelength marking provided on the chart, you can find out this to be equal to lambda by 5 or 0.2 lambda starting from this point, and you stop here. So, you can now read out the impedance at this point. So, you can see that it is closer to a circle which will be around r equal to 3 and j is equal to approximately, in actual Smith chart you can read out the value. So, in that way you can find out the normalized input impedance and then you multiply it by Z naught, that is 50 ohm, and then you get the actual impedance seen at this point. The impedance at any intermediate points can be also seen. For example, if we stop at this length, then we get a input impedance of 1 plus J 2, that means here it is 50 plus J 100 ohm. Now, we can see that starting from the load, as we move down the line, we cross this axis, that means here the input resistance become purely resistive. So, let us consider another case when ZL is 10 plus J 25 and Z naught is 50 ohm, and we have seen the normalized impedance is 0.2 plus J 0.5. Now, YL 1 by ZL is 0.69 minus J 1.724. Now, how we can mark this YL directly on the Smith chart? So, we start with marking ZL and then we draw the constant VSWR circle. Then if we pass a line through the center of the Smith chart where it touches this circle, this point gives us YL which is equal to 0.69 minus J 1.724, and here you can see the values are close and from the actual Smith chart it can be read out. Similarly, if we drop a line from here intersecting this axis, then the point where we touch the constant VSWR circle will give conjugate of ZL. So, this Smith chart starting from a load point, we can plot the YL, we can plot ZL bar. Please note that when we are using this chart as a impedance chart, this point on the chart will represent the short circuit point, because here ZL becomes 0 and this point will represent the open circuit point where both RL and XL becomes infinity. We have seen some basics of the Smith chart. We will use this Smith chart in our later lectures extensively, particularly when we will be solving the impedance matching problem. So far we have confined our discussion to transmission lines. We consider another type of waveguiding structure which are in the form of hollow metallic pipes of rectangular or circular cross section. These are called rectangular and circular waveguides. So, our next lecture will start with the discussion of this type of waveguides.